Okay. So can I also ask you to just quickly put, maybe not, no, not needed. You know, it's always challenge to take attendance, you know. So maybe I simply take a screenshot. Okay, good, done. Is there a shortcut for, maybe there should be, from the keyboard when you know, on Windows you have print screen, you just press print button and it would save it will take the screen capture.
Yeah.
What's on Mac?
Oh, God. No, but asking me, I've never used a Mac.
Oh, okay, I see.
Would it be Control P or something?
No, that would Control P.
Oh, that'd be
Command P. Command P would print it, and
Command Shift 3.
Command Shift 3. Ah, good one. That's good.
Excellent.
Fantastic.
Thank you, Google. Google, very helpful.
Oh, lovely. Yeah, that's good. That's good. That will do.
Very happy.
And we have 3 minutes before we start. Any of you have any questions so far for me? Well, lecture 3, as you know, was half of that was recorded, half was not. So what I did, I recorded first half of the lecture and uploaded that on LMS. It is in the folder, Zoom recording folder. Please have a look. If you want to see the first half of the lecture, then it is there. First half and second half now combined. It is all of it. Another thing which I actually, last year recordings, I forgot to mention that actually first 3 lectures were missed, and 4th lecture, the video was not recorded. After that, it's a study. There was something wrong with the echo recording at that time, so it was not recording, but we have recording for 2020 lectures anyway, so that will supplement everything. Yeah. Any questions, anyone? Okay, no questions. Yeah, so today we have a tutorial as well. When we finish, we'll start soon after when we finish our lecture. And in the tutorial or practice class, what we do, we would go over some exercises. And what I do normally in practice classes, I split in different breakout rooms. I mean, there will be groups of 3 or 4 students in one breakout room. And then, yeah, in that breakout room, we would go over the practice classes, yeah, and see, do some exercise, to be precise, exercise 2 this time. Yeah, if you haven't done that already, we'll do them again, and I will be there to answer your questions. Okay, all right, so let's start today's lecture. And today what we're going to do, in lecture 4, we're going to do some arithmetic. Mostly we'll do binary arithmetic and computer representation of integers. That means how integers are stored in computers. And in next lecture, we'll talk about storing real numbers in computer. All right. Okay, so starting with arithmetic in decimal basis. So what we did previously, we discussed addition and subtraction of binary numbers. And for example, now if I want to add this number 1011, these are both binary numbers. If I want to add them, so I would 100. What I would do, the process is the usual process of addition that you have done for the decimals at school. Now here, every time when you're adding, subtracting, we'll do multiplication and division as well today. There only, it's like a puzzle, you know, you're only allowed digits, zeros and ones. Okay, you cannot go beyond that. So if you're adding numbers within binaries, the only restriction you have, you are only allowed zeros and ones, nothing else. So following the same principles as we've done before, we're going to add, subtract, multiply, and divide numbers in binary. For example, if I want to add these two binary numbers, what I'm going to have, then I would do this. 1 plus 1 is 2. I should not say 2, it's 1, 0. So you would have 0 here, and 1 would go to the next, carried forward. So 1 plus 1 is 1, 0, plus 0 is 1, 0. So 1 goes there. So 1 plus 0 is 1. So you have this. Then 1 plus 1 is 1, 0. And 1 plus 1 is again 1, 0. So my answer for this would be 1, 0, 0, 1, 0, 0. All right. You can also verify this answer by, if you like, you can convert these numbers into their corresponding decimal numbers. For example, this number would be what this equals to? A 2 to power 0 plus 2 to power 1 plus 0 plus 2 to power 3. So that would be 8 plus 2, 10 plus 1, 11 plus, if you want to add those numbers, those would be 1, 2, 3, 4, 5. So this is 2 to power 4, 16 plus 8, 24 plus 1, 25, which is equals to 36. And if you want to write 36 in binary, so converting 36 in binary would be 18, 0, 9, 0, 4, 1, 2, 0, 1, 0. As you can see, this is 1, 0, 0, 1, 0, 0. So the answer that we've calculated here is correct. Okay, so that's how we've been adding numbers. Similar method extends to subtraction. Again, if you want to subtract two numbers, you do this, put a higher number up there and lower number down there if you want. Okay, the left numbers up there and the right on down here. So you would have 0, 1, 1, 1. And what you're going to do, you're going to subtract them. And subtraction works similar to what we the system that we did before, like like in decimals. So 1 minus 0 is 1. Okay. Then 0 minus 1 is not possible, so I would take 1 from here. So this number would become 1, 0. 1, 0 minus 1 is 1. So this 0, since I had moved this 1 to the right, so this converted into 0, right? Now I have to subtract 1 from 0, not possible. So I would take this one all the way up there to convert into 1, 0. 1, 0 minus 1 is 1. So this was 1, 0, but I had moved 1 to the right, so it became 1 now. 1 minus 1 is 0. And then this was 1 as well. So 1 minus 0 is 1. So hence my solution, this subtraction is 1, 0, 1, 1. Again, if you want to verify, you can do so by converting this number into decimal, that number into decimal, subtract them, and then whatever answer you got, you convert that into binary to verify this. Yeah, let's do that quickly. What this number is, as you know, it is 1 times 2 to power 0 plus 0 times 2 to power 1 plus 1 times 2 to power 2, so on. I would have then basically 1 plus 4, that makes 5, plus 0 plus 0 plus 32, that makes 37, I think. because the last number is 1, 2, 3, 4, 5, 6. So its last number is 2 to power 5. This is 2 to power 2. That is 2 to power 0. So 32 plus 4, 36 plus 1, 37. And this number is 2 to power 1, 2 to power 2, 2 to power 3. So 8 plus 4 is 12, plus 2 is 16. And this number, oh no, I have to subtract them. So subtraction, 37 minus 16 is 21. And now you can convert 21 into binary. So you can do again the same process by successive division. So 10, 1, 5, 0, 2, 1, 1, 0. So your answer, oh, what did I do?
It's 14, not 16.
Well done. Thank you, mate. Thank you. Wow. So you have 11, 1, 5, 1, right, 2, 1, 1, 0. So hence it is 1, 0, 1, 1 to the base 2. 1, 1, 1 to the base 2. Well, in doing these arithmetics, these you know, sometime these addition and subtraction, these typos happen. So always be on your toes. You know, try to make sure that you don't repeat similar kind of mistakes as I do sometimes. Right. Okay. There's an exercise, calculate the subtraction. So, but you know the method now, right? Rest of all of these examples can be generated, and there could be hundreds of them, thousands and millions, whatever numbers you want to generate, you can do so. Right. Let's move on. The next step is to we've done addition and subtraction. How about multiplication and division? For binary multiplication, the basic table is very similar, very simple. Now remember, always you're only allowed zeros and ones. Okay. In fact, I regard these arithmetics simpler than the arithmetics that you do in decimals. For example, if I want to multiply 0 times 0, it is 0. 0 times 1, it is 0. 1 times 0 is 1. 1 times 1 is 1. Yeah. So yeah, that's how these tables work. So long multiplication is a similar method as we just did now. So let's look at some examples. Okay, so let's multiply 10111 with 1101. Okay. How many of you remember long multiplication? I understand most of us been used to of calculators. So whenever somebody asks us to multiply 113 with 23, let's say, we'll just jump on a calculator and do that. But on a piece of paper, if we are doing, we need to know, for example, if I am doing this number, how we would multiply. I would multiply 3 with that string. So it would be 9, 3, 3. And then this first number is 0. And then I multiply 2 with that string again. So 2 times 3 is 6, 2, 2, and I add them up, 9, 9, 5, 2. So this is my, this is how the long multiplication works. Similarly, if you're multiplying with 3 digits, 4 digits, or 5 digits, same process extends. Now here, what I'm going to do, I'm going to multiply 10111 with 1101. How it works? So you put a number, this number up here, and then 11011 here, and then you multiply. Now you can see either the string would be 0 when I'm multiplying, or it would be the same. For example, when I'm multiplying 1 with this string, what I would have 10111. Yeah. Then you multiply with 0, but that would be a 0 string, so we can skip it and move on to multiplication of this 1. So now when you're multiplying this one, which is a third digit, so first two are zeros here, and then you're multiplying 1 with all of them. So you would have 1, 0, 1, 1, 1 as the string here. And similarly, when you're multiplying this 1, so you would have first 3 zeros because you're going to skip 3 spots, and then multiply that, so it would be 1, 0, 1, 1, 1. And then what we do, we just sum them up, all of them. 1 plus 0 is 1, right? Then 1 plus 0 is 1. 1 plus 1 is 1, 0. Plus 0 is 1, 0. So what happened? So of this 1, 0, I put this 0 here and to take this 1 up here, yeah, to the next column. Then 1 plus 0 is 1, plus 1 is 1, 0, plus 1 is 1, 1. So of this 1, 1, I'm going to put this 1 here and carry remaining 10, which is, remaining 1, sorry, there. So, wait a minute. So I would put 1 here and take this 1 to the next column, yeah, here. Now again, 1 plus 1 is 1, 0, plus 1 is 1, 1, plus 1 is 1, 0, 0, 1, 0, 0. So of this 1, 0, 0, this 0 goes there, and remaining 1, 0 would be carried forward. Now remember, at one step, I am only allowed to enter 1 digit, not 2 digit, unless it is at the last one. So now 1, 0 plus 0 is 1, 0, plus 1 is 1, 1. So of that 1, 1, I would put 1 here, and 1 is carried forward. So 1 plus 1 is 1, 0. Of that, 0 stays here, and 1 goes forward. And that 1 plus 1 is 1, 0. So you would have 0 here, and 1 carried forward, and there is nothing, so 1 stays the same. So all of this gives us multiplication to be 1, 0, 0, 1, 0, 1, 0, 1, 1 to the base 2. Okay. Again, we can always verify this. If you want to verify your answer, there is always an option of writing them in terms of decimals and then converting them. For example, this number is 1 plus 2 is 3, plus 4 is 7, plus 16 is 23. That number is 1 plus 0 plus 2, no, 1 plus, that is 0 plus 4, 5, plus 8, 13, yeah? Now 13 times 23, long multiplication you can do, that would be 96992. So this number is 299. Now, all right, so this number has to be 299. In order to verify that, we can do we can convert 299 into binary, same way as we have done. So we would have 1, 9, no. Yeah. So it would be 1, 4, 9. The 1 is the remainder. Then you would have 7, 4, 1 is the remainder. Then you would have 37, 0 is the remainder. 18, 1 is the remainder. 9, 0 is the remainder. 4, 1 is the remainder. 2, 0, 1, 0. So hence my string is 1, 0, 0. So 1, 0, 0. Then I have 1, 0, 1, 0, 1, 0, 1, 1 to the base 2, which is the same as this one. Again, this is just for verification purposes. If you want to verify your answer, in a nutshell, what we want to do, what I want to explain is that the methods of multiplication is the same as the long multiplications you have done before. Right. Any questions, anyone? All right, no questions. I mean, if something is not clear, please stop me at any stage. don't have a luxury to see face to face and see from faces whether you're understanding the concept or idea or not. We're in a different environment where we are learning from each other. So here, from my lecture, what I want to get is that I really want to know whether you're understanding those ideas or not. If you're not, then please stop me and ask me again. Yeah, I'll happy to explain it again and again if you want. Yeah, thanks. In a face-to-face lectures, that's what I normally do. Actually, I ask questions from students, and that keep them always focused. You know, I ask questions, I engage with the students and all that. But now we are in sort of a different environment. So here I need your cooperation on this. Now. Similarly, if you want to multiply this, you can do so. So I leave that as an exercise for you. Now we move on to division. So division, again, as I said, division is similar as we've done the real divisions before. For example, if I want to divide these two numbers, okay, the easiest way to remember is that at each step, you are only allowed zeros or ones, nothing else. So it is actually simpler than real. For example, now if I ask you to 735 divide by 7, how you would do that? Yeah. Okay. So we would divide this first digit by 7. So 1 times that, 7, subtract is 0. Then bring this 3 down. So 3 and 5, both the digits down, 35. Now I want to divide them. So on 3, 7 divided on 3, not possible. I'll put a 0 here. Then 7 divided on 35, combine them together, is 5. So this is 35. So remainder is 0. Or let me put that. Suppose you want a number 29 and you want to do let's say 129 and you want to divide on 5. So first time when you're dividing, if 1 is not possible, you combine both the numbers. So it's 12, 5 2s are 10, remainder is 2, right? Then you bring this 9 down, so it becomes 29. 5 times 5 is 25 and remainder is 4. And after that, this is not possible. So we move on to then the decimals there. I mean, point fractions there. So in the fractions, you can add as many zeros as possible. So you put 0 here, and 5 times 8 is 40. And when you're dividing 129 over 5, your answer is, so you're dividing 129 over 5, and your answer is 25.8. These methods you learned at school a while ago, so you may have forgotten, but we are trying to remember them again now. All right, so using the same principle, now in this principle, when you are multiplying this 2 with 5, you have all the options, 5 times 2, 5 times 1, 2, 3, 4, all of these possibilities are there. And similarly, for example, 5 times up to 8 and whatever numbers you can multiply that. But when I'm dividing with binary, I don't have the luxury of using all the digits. I have only zeros or 1 option. So it makes slightly things simpler. What I mean there is, if I'm dividing now 11101 divided on 110, how I'm going to do that? So first of all, 110, I multiply that with 1 to get 110, and now I subtract it, all right? Now when I'm subtracting, 1 minus 0 is 1, and after that 1 minus 1 is 0, 1 minus 1 is 0, and I don't have to write zeros on the left. So the difference is 1. As you can see, this number is 7 minus 6, it has to be 1. Now, 110, so what's the next step? You put next digit down here, 0, and then divide with 110. Not possible, so you put 0 up here. And then you bring down this one here, 101. 101 is still smaller than 110. I still can't divide, so I have 0 here. All right. And then up to so on. I bring this 0 down and put decimal there, 1010, and now I can divide 110. Yeah. Does it make sense, everyone? Yeah. So this is 0. Yeah, that is 0. And then this is 1. Yeah, 100. Now, so the next step is to bring another 0 down, put it here, and 1 would go in there again, 110. Yeah, so 0 and 1 is the, after subtraction, that would be that. And then I bring another 0 down, but I still, now 100 is still smaller than 110, so I have to put another 0 and bring another 0 down. And now again, that process continues up to so on. So when I'm dividing this number, 110, 1 divided by 110, it is 100.110. And then it is continuing, it is not terminating, so that is my division answer. Okay, so with 3 bits after the point, I have this. Does it make sense, everyone? Any question or anything that you want me to repeat? Yeah. Okay. All right, if not, then okay, the purpose of explaining multiplication, division, I mean, this arithmetic is just to explain that, that the process that you learn at school is the same, with only now we have some restrictions that we are only allowed 0s and 1s and nothing else, no other digits. So how we adjust this whole process. So the puzzles of the piece are that, okay, in this puzzle, you're only allowed 0s and 1s, and then how you would do the arithmetic. Yeah. Anyway, the solution is there again, so please practice as many questions as possible. As I described, it may appear slightly awkward, but actually division calculations are very simple because at each step of the division, the divisor goes into the number either once or 0 times. There are only 0 and 1 possibilities, so you don't have to think of numbers that you multiply with to get the number. So the options are already there, 0s or 1, nothing else. Yeah, so that makes it slightly simpler. Now think of this calculations. Let me actually do this for you. 110, 111 divided by 101. Now when I'm doing this, since it's a 3-digit number, I would choose the first 3 digit and it will go once. Yeah, 101. So when I'm subtracting 101 from 110, what I'm going to have, so this is 10 minus 1 is 1, then this converts into 0, 0 minus 0 is 0, 1 minus 1 is 0, so this is 1. Then next step is to bring this 1 down to have 1 here, all right? Actually, oh, no, what happened? Okay. Then this 1 down to have 1 here and divide with 101. Now I still can't do it, so I would put a 0 here and then bring in another 1 here. So now I can divide, and as I said, this divisor can only go into 0 times or 1 times. Yeah. So 1 times that number 101, okay, what I'm going to get then, the difference is 0, 1, and then I'll bring this one down here to get 101, and 101 in 101 goes once only, and this is 0, so the answer would be 1011 to the base 2, right? So this is how this entire division process works. And the same process you can apply. You can actually recheck your answers by converting this into decimal, that into decimal, divide them up, and whatever answer you have, convert that into binary to verify that it is the same. Okay. Right, okay. Now, the next step is, so far what we did, we learned, okay, we have binary representations, and within binary strings, you have binary and binary if you want to add them, how addition work, if you want to subtract them, how subtraction work, how multiplication work, and how division work. Now, what we want to look at, how computers actually store numbers, how they represent them. So if you punch in integers, for example, like 2 or 3 or 5 or 10 or something, then how these are stored in computer. Remember, they are okay. So a computer works in bytes, right? And each byte is 1 byte is equals to 8 bits. So 8 bits are, 8 bits are, if you have 2 bytes, then it would be 16 bits. So we look at the shorthands for binary, which were octal and hexadecimal. Now, if you want, did anybody say something? Okay. So now we actually look at if I type in a number, let's say integer, then we convert that into binary, how that binary is stored in bytes, how that number is stored there. So it could be positive number, it could be negative number, and there is whole sort of range of them, and how that works. So what we did so far, we look at the binary number system and its useful shorthands, octal and hexadecimal. And we looked at the number of ways it can be, manipulated on arithmetics with that. So we are now going to look at how binary numbers are stored and manipulated in a computer. The process works differently for integers and differently for fractional parts, like any real numbers. Yeah? When there is a decimal involved, then the process is slightly different, and when there is an integer, process is slightly different. So we deal with them individually or separately. Okay, so let's look at now computer representation of integers. Recall that in a computer, an integer is stored in a sequence of bytes, where 1 byte is 8 bits. All right. So 1 byte is 8 bits, and what we want to do, we want to look at how integers will be stored in the sequence of 8 bits. Yeah? So for manipulating numbers in the processor, normally we use 4 bytes or 8 bytes. These are typical processors that are common nowadays. So, but we would stick with, for convenience, we would stick with 2 bytes only. That is 16 bits computer. The principles are the same for 4 bytes or 8 bytes, whatever you choose. Okay, now with 2 bytes, what's going to happen? The storage of an integer can be pictured as, so integer will be stored in these 2 strips, where each one this is 1 byte, that's another 1 byte. Okay, and we want to store our integer in that. In other words, total bits available are 16 bits. Okay, naturally you would think that, okay, what if my integer is, my number is negative? Or what if my number is positive? So for that, that means we have to keep in mind that how it's going to handle such a number. Yeah. Okay, so let's look at firstly what sort of numbers, what sort of integers can be stored on 16 bits. Now remember, each bit is either 0 or 1. Yeah, there are two possibilities on each box, in other words, and there are total 16 boxes. All right. So the range, that's the total number of different integers that can be stored. Is if there are, okay, there are two possibilities here, two there, up to so on. So in other words, there are 2 to power, since there are 16 boxes, there are 2 to power 16 possibilities. So actually you can store 65,536, all right, different integers, numbers in 2 bytes. So what that means, so the integers in the range from 0 to 65,535, so that makes total 65,536 integers could be stored in 2 bytes. It's your choice normally. I mean, some people, they deal with just positive numbers and say that we can store from 0 to 65,535, and they call that as signed or unsigned. Yeah, I think unsigned representation. So it is preferable to have about the same number of negatives as positive integers. So this is the signed representation. So subtraction can be carried out, in other words. So, all right. So in 2 bytes, we can store at most, or represent at most, 65,536 different integers. So the range is from 0 to 65,535. So what we do, we actually split them into half. Half goes towards negative side and half towards positive side, so that we can store them. So for this reason, we split them negative 32,768 and positive 32,767, and then 0 is there, which we normally don't assign any sign for zeros. So when you put all of them together, that would be your combined range. So in other words, you have a real line, 0 here, negative 32,768, positive 32,767. In between every integer number that you have, we can we can store it, right, or represent that in binary. So in other words, this number is 2 to power 15, and this number is 2 to power 15 minus 1. Right? Now on a 4-bit computer, if you have 4 bytes available, you would have, the range would be negative 2 to power 31 to positive 2 to power 31 minus 1. And with 8 bits, it would be slightly, it would be a lot bigger than that. Yeah. Okay. Now we come on to storing an integer in 16 bits. How are we going to store a number in the range negative 32,768 to positive 32,767 in 16 bits? How are we going to do that? So first thing, we need to know whether the number is positive or negative. So what we're going to say that, okay, the first bit is the sign bit. So we always assign that, okay, in this, these are 16 bits. The first bit would be the sign bit. So sign bit means, now if the number is positive, we will have 0 there. And if the number is negative, then we're going to put 1 here. If the number is positive, we put 0. If the number is negative, we put 1 there. Yeah. Now, if the number is positive, you're going to put 0 in the first box, and the remaining 15 boxes is the binary representation. If the number is negative, first bit is 1, and remaining 15 bits is the binary representation of that number plus 32,768, so that you have converted that into a positive number. I would come in a bit. There is a simpler way of representing this, which we'll deal with towards the end of the lecture. But for the time being, what that means, if you have a negative number, first bit is 1. So as soon as it reads 1, that means a negative number. And remaining number that you have, what you do, you add this number 32,768 in it and convert that into binary. That would be your representation. So this method for storing negative integers may seem to be unnecessarily complicated, but it leads to a simpler process for arithmetic as well. So let's look at the positive number representation first to start with. Find the 16-bit computer representation of this decimal number. So remember, this number is way less than 32,767. So this number can be stored in 16 bits, right? Or 2 bytes, in other words. So first thing we need to look at is what is its binary representation, right? And okay. And since this number is positive, so I have these boxes. I've done that question, so let me actually move on. Okay, never mind. Okay, so the given number is positive, so convert it to binary, and the binary conversion of this number, as I said, just keep dividing with 2 and noting down all the remainders, and this is your binary representation. How many numbers are these? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So these are 14 bits. However, what I am after is the 16 bits in total, where the first bit is for sign, but that means I need 15 bits for that. So what we do to make it 15 bits, we add a leading 0 in it. So we have these 15 bits. Hence this number 12,723, its binary representation is this one. And when you store it in computer, since it's a positive number, the 16th bit, we would have a 0 here as well. So this is the sign bit that represents as a positive number. And remaining representation is the binary representation of 12,723. So this is how it stores numbers there, right? Any questions, anyone? So pretty much straightforward process in this. By the way, I forgot to mention, since so this answer is regarded as a computer representation of this number rather than the binary form. So we don't put index 2 there. So when we are representing that, we don't have to put it's just a convention. Yeah. Now we've done with positive. Now to deal with the negatives. How are we going to deal with the negatives? Remember, if the number is negative, first bit, so since this number is negative, first bit that we're going to have is the sign bit. And if I'm going to, so 1 would go there, right? And then this 1 indicates that this number is a negative. Now remaining 15 bits from here to here, 15 bits are binary representation of -7132 plus 32,768. Remember the range on the negative side. So what we are going to do, I'm going to look at its positive counterpart when I'm looking at its reflection. So I would add translation by 32,768. So when I add them up, I would get 32,768 minus 7,132, 636 and 25. So 25,636. And then what I want to do, I want to convert that number into binary. Okay, and whatever that binary representation would be, that would go here in this 15 bits representation. So what I mean there is, so I have this number, I would convert that into binary, and that binary representation, since that is already 15 bits, I don't have to add any leading zeros because it's already 15 bits. So I would put this 1 as the sign bit, and remaining 15 bits are these. Okay, so the only difference between representation of a negative integer from the positive integer is that you simply add 32,768 so that we could store it here. However, this is not the only method of representing numbers. There are other methods as well, and quite simpler. All right. Okay. And how those methods work? Right. Okay. So let me go on and explain that and why those methods are preferred methods as well. So the method is called 2's complement, and how it works. Remember in the previous example, what I did, I had to add 32,768 in it to get the binary representation. However, there is a quicker method that I can apply, and that method would be simply convert this 7,132 into binary first to start with. 7132, I convert that into binary. I would have 3, 5, 6, and 6, remainder is 0. And then I would have 1, 7, 8, 3, 0. I have then 8, 9, 1, remainder is 1. 4, 4, 5, remainder is 1. 2, 2, 2, remainder is 1. 1, 1, 1, remainder is 0. And 55, remainder is 1. 27, remainder is 1. And then I have 13, remainder is 1. 6, remainder is 1. 3, remainder is 0. And 1, remainder is 1. So I would start from here. I have 1, 1, 0, 1, 1. And then I would go all the way. I have 1, 1, 0, 1, 1, 1, 0, 0. So this is my, so far, the binary representation of 7,132. Let's count digits. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So these are 13 bits, but I want them to be 15 bits, so I would then have zeros and zeros there. Okay. So in order for the 2's complement to work, now look, this is the actual answer, but I want to look at the shorthand method of converting these, representing these numbers into binary. So the method is 2's complement. What it says that, okay, convert this number into binary and write down the 15-bit representation. And then what you do, you simply, what happened? Okay. Now if so all the trailing zeros and the and the first one that you have, write that as it is, okay? And then all the remaining bits, flip them or take their complement, right? So this would be then 1 becomes 0, the next one becomes 0, this 0 becomes 1, this 1 becomes 0, 0, 0, 0, 1, 0, 0, 1, 1. Simply switch them. Now you see, this is exactly the same as this number. So this method is called 2's complement, and this is actually quicker than adding 32,768 and doing that. It's quicker that we do the binary here, and then what we do, all keep trailing zeros and the first one that appear on right, and then switch the rest of them to take their complement. So that would be the same as finding the representation of any negative number. Yeah. So the solution is there and the method is explained. So I just wanted to do that example in real time instead of just present those typed up answers. Yeah. Okay, any questions, anyone? So we can look at more examples that might actually explain this process a bit more. Find the 16-bit computer representation of this number. Right. Okay. Now, for convenience, I have written this binary representation here. So it's basically, it says it is negative of 2,641. Now, how many bits? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So I would add 1, 0, 0, 0, 1, 0, 1, 0, 0, 1, 0, 1, and then add 3 zeros in it to make it 15 bits, right? So this is my 15-bit representation of 2,641. Yeah, it's the 15-bit representation of that number. And now what I want to do, I want to represent this number. I want to store this negative, since it's a negative number, I have to use the 2's complement method to start with. Now there are no trailing zeros here. So I would keep this first one as it is, and then all of these numbers, I would just switch them. If it's 0, I will convert that to 1. If it is 1, I convert that to 0. So what I would have then, 1, 1, 1, 0, 1, 0, 1, 1, 0, 1, 0, 1, 1, 1. So this is my 15 bits representation of 2's by 2's complement. And since the number was, this number was negative, so the first sign bit is 1. So this would be my then 16-bit representation of the number negative 2641. Yeah. Does it make sense, everyone? Yeah. So, well, great, thank you. So here is that, as you can see, this 1 as it is, and then 0 goes to 1, that 0 goes to 1, this 0 goes to 1, that 1 goes to 0, this 0 goes to 1, and so on. Yeah. So when using 2's complement method, leading zeros must be included. I mean, you have to have 15-bit representation first, and then apply the 2's complement. You cannot apply 2's complement if your bits are smaller than 15 bits, okay? You have to have 15 bits there, and of course, 1 bit is the sign bit. We include that towards the end. Now, find the 16-bit computer representation of negative 32,768. Yeah. Now, this is a sort of a trick to trick you here. So it's just a question for you. Now, what you think would be the representation of this number? Anyone?
0, I guess.
Yeah, 0, 0, 0, 0, 0, but it's how we would show that it's a negative 32,768.
You'd start it with a 1
Yeah, why would do that?
because it's negative. And that's how the computer reads it.
Yes, exactly. That's precisely the right answer. So if you negative 32,768, and if you add 32,768 in it, you got 0, right? And 0's 15-bit representation is 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. This is the 15-bit representation of this number. And then this digit there to indicate that it was a negative number. Yeah. So, and if you want to use 2's complement, you can do so as well by writing binary representation of this number, which would be sort of, you know, yeah, whatever that appears up. And yeah, you apply that. So which would be actually basically this one. All the weights would be 2 to the power 16 or 15. Yeah. Anyway, that's how we do this. Finally, an exercise before we conclude. We have a couple of minutes that we can do. Find the 16-bit computer representation of this number 5,132 with a negative. So I've written this binary representation of 5,132. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So again, this is 13 bits. I have to include extra zeros here. Yeah. And then I apply 2's complement. So I would have 1, 0, 0 as it is. I mean, trailing zeros, and then the first one as it is. And then I'm going to switch them. 1 becomes 0 and zeros become 1. Yeah. And this is 15 bits, but since my number was negative, I would put 1 there as well. Yeah, so that is my 16-bit computer representation of negative 5,132. Yeah, so as you can see, 100 is the same as 100, and rest of the numbers are switched until that. And then since it was 13 bits, I had to put 2 zeros there, and those 2 zeros becomes 1, 1. And this first one is the sign bit to say that it's a negative number. Yeah, that is it for today's lecture. In the next lecture, we will go over representation of you know, how we're going to store negative numbers as well. So we would require 32 bits to do that, and lots of other things. Any questions, anyone? No? Okay, so I'm going to then stop recording, and then we are